Hi everyone, I'm Guillaume Klein. I'm the main developer of OpenMT and also a research engineer at SYSTRAN. So during this talk, I will review 1 year of developing OpenMT and maintaining it. So of course, 1 year is very short for machine translation. The best example is SYSTRAN that has origins back to 1968. But actually 1 year is quite long for open source, with the main problematic of how to keep people interested and invested in your project. And most importantly, 1 year is very long for deep learning, and you know it. A lot of things can happen, including new frameworks, new hardware, and new models that really change the way you work and interact with this approach. So this talk is not only a review of the year of developing OpenMT, but it's also an attempt to answer this question: why is OpenMT still relevant 1 year later? So it's a story in many chapters, and I will come back to many elements of this response. So the first chapter is to build on strong basis. So of course, this basis was mentioned by Sasha. It's the seek-to-seek attention project that was developed by Yoon Kim. And it was very interesting because at the time it was already very efficient, state-of-the-art, and very easy to use. And for this kind of project, I mean deep learning project, it's not common. So that's why at SYSTRAN we were very interested and motivated to contribute to this approach. And it's important to know that OpenMT is not only an inspiration of this project, it's actually a fork. That means OpenMT is built on it, and there is a strong legacy that you can find in the code, including the way we build the network or including the variable names in the code. So the legacy is very strong on this part. That was the first chapter. The next chapter is to grow fast. And I think the best example to that is the number of code commits. So I used to take this indicator of activity. We can see at the beginning there is the seek-to-seek attention period with fairly low activity, and then we started working on OpenMT, and we saw that the number of commits really increased a lot. And that shows that we were, very motivated to add a lot of features. Jean was also very motivated, and in a short amount of time, we added lots of new features, including but not limited to the tokenization tools, new encoder types, multi-GPU training. We also added translation servers, input vectors to train speech models, and validation metrics, and also more recently, dynamic dataset to handle very large data storage. And all these features were released in many versions, actually 9 versions. You can find the details of each release in a changelog file, and it was very it defines a really good set of features each time we release a new version. And of course, this quick growth poses lots of new challenges. First, within the code, there is a growing complexity, and we simply accept this fact. We always prioritize merging pull requests fast. That means we prefer having a lot of features and over, for example, a complex and long code review process, and we accept that. We also needed to take care of the versioning semantic. So you saw some version number. Actually, there is no real semantic on it because we are still not V1, and V1 usually indicates stability. But actually, we have some untold rules about the versioning, and I think they are very important to the way we manage the project, and they are also key to the success of OpenMT. The first one is to never break model compatibility. And I think that's a huge part of OpenMT, is that, for example, you train a model with the version 0.2, and it is still working today. So you can start building lots of models and keep them around and keep serving them, for example, in your company or to your users. The second rule is to not break translation APIs unless required. So that's also very important for industry, where you integrate OpenMT within your code and you want things to stay stable. The third rule is to avoid breaking option names. Again, that's similar. People are writing scripts using OpenMT, and you want them to work in the long time. And all these rules, I think, are very important and makes OpenMT usable in the long term. And the fourth rule is actually not a rule, is that we didn't provide any stability guarantees for the code itself. That means if you are working against, for example, the APIs on the encoder, you are not guaranteed that it will work on newer release. And overall, we have a difficult balance between the research interest, the industry interest, and the user interest, because all this category wants different things from the model. For example, the researchers want custom models, an advanced training flow, and an overall extensibility of the project. The industry wants robustness, stability, and also an easy integration of it in their software. And the user wants an ease of use of the project and low hardware requirements. And we try to cover all use cases. And I think we managed to do that because OpenMT is used in many research papers. Some companies are using it, and many users find it easy to set up and use. And to find it easy to set up and use, we compiled a lot of documentation materials. So not only a listing of available options, but also very high-level and user-friendly documentation on how to use the project. So I think that was very helpful to users to get into the project. And we also provided a very complete user support. I mean, we had a goal to answer and fix issues fast. So if you go to the forum, there is a support category, and it's very active. I think that's the most active category on the forum. And I think we were very efficient at assisting users and fixing issues quite fast. And that's why people, I think, were still around the project for a long time. The next chapter came quite quickly, is that we started extending the core project to other projects within the ecosystem. The first one was image-to-text that was developed by Yunse and Deng. And I think there will be a presentation this afternoon, so stay tuned for that. So it's a deep learning based approach to learning image-to-text conversion built on top of OpenMT. So that's very interesting because it's using OpenMT for something very different than text translation. Another project that we released separately is the tokenizer. So we had some tokenization tools within the Lua code, and we separate this code into C++ code. So that means you can include this approach within your existing products and run OpenMT style tokenization. And we also added Python bindings, so you can also use this code within other frameworks like PyTorch or TensorFlow. And we are still working on improving this integration within existing frameworks. And this is, I think, a very interesting project. It didn't have a lot of success, I think. It's called C-Translate, but I really liked it. I mean, I'm very biased because I developed it, but I think it's nice. So it's somewhat an inference engine for OpenMT models, so the Lua version, of course. And it's based on Eigen, the linear algebra library. So the idea is just to load the model, read and build the graph with C++ code, and execute it with Eigen. So actually, there are some interesting use cases, and at SYSTRAN, we actually use it in some products. For example, you can do transliteration in internal NLP library because you don't want to include, for example, Torch or Lua within an existing library. So this is a very nice example of integrating NMT models within a developer library. And we also used it for some demo translator on mobile phones or more generally embedded devices. But I think its success was limited due to its limited GPU support. And when you want to run a full NMT model, you actually want to use a GPU. And so that's what is lacking from this project. And NVIDIA has put also a lot of work to provide this kind of inference engine. And so maybe you can take a look at that. The next chapter came quite quickly in the development of OpenMT. I think it was about 2 months after the first release. And we already needed to catch up with deep learning frameworks. And at the time, it was, of course, PyTorch that was released in February 2017. And for us, it was a bit strange because it was only 2 months after the first release, and we already had this feeling that our software was outdated. But I mean, that's the deep learning thing. I mean, we need to work with that. And actually, we didn't need to catch up at first because it was done by the PyTorch developers that released a light version of OpenMT in PyTorch, mostly as an example of implementing NMT with this framework. So it was proposed by Adam Lehrer from Facebook and Brian McCain from MetaMind, and they released a very simple version of this project. But a few weeks or even months later, we took the project in charge, and we added lots of new features, including the transformer model, the convolution approach, new type of cells, and also advanced attention models. And that thanks to many active users that are here today, and we also give a presentation this afternoon. For example, of course, Sasha, that is maintaining the project, but also Ben Peters, Janu, Sebastian, and I know that others are here and participating in the development of OpenMT PyTorch. And I think today it's the most active community in OpenMT. As you can see again, the number of code commits in OpenMT and the PyTorch version, you can see they have a similar evolution, and more recently a very active dynamics around the PyTorch version. And I think it will continue this way, and we'll see that you can do very interesting things with the PyTorch version this afternoon. The next chapter is also interesting and maybe surprising for some people, is that we started diversifying our offer in terms of open source software. And it was about releasing a TensorFlow version of OpenMT. So this was quite recently, around November 2017. Again, for this part, I'm also biased because I'm the only developer of this version, but I think it's worth talking about. So like the other version, you can do, of course, machine translation. That's the main task. But of course, more generally, sequence-to-sequence mapping, sequence tagging, and classification. And I find it interesting because I designed it from scratch, and I learned many things from the first version of OpenMT. So I think it's, I mean, that was the goal, to design it right this time. And in particular, I chose to go with a very modular design. So instead of giving a long options on your command line, you just give a model file, and this file is actually a Python file where you need to build an actual Python objects that describe your model. For example, in this case, we are building a sequence-to-sequence model where you define a certain type of input at the source, a certain type of input at the target, and you define also the encoder objects and the decoder objects you want to use. And actually, it doesn't limit to that design. I actually introduced some generic building blocks that you can reuse and combine together. For example, you can have multiple inputs in parallel, so that means several files that you can feed into your network. You can apply a mixed input on one file, that means usually several embeddings that you compute in parallel. You can also pipe encoder together. For example, start with RNN, then you feed the output of the RNN into a convolutional layer. And you can also use parallel encoders. That means you encode multiple inputs in parallel. So I think that's interesting, and you can use that to build very crazy models. For example, here is an example. It's not a real example, but it shows that you can model very complicated architecture. For example, here I define a parallel input that takes actually 2 files. On the first files, you compute a mixed embeddings composed of the word embeddings and a character level embeddings. So that's the first input. And you concatenate these 2 embeddings. And the second file, you just read a record of values. So at this point, you have 2 inputs to your network. And then you can customize your encoder to actually exploit these 2 inputs. So the first, you will apply a self-attention encoder. On the second while, you apply a pyramidal RNN encoder. So at this time, you have 2 encodings that you will concatenate on the time dimension. So that's the first encoder, and you have 1 encoding at this time, and at the end, you feed that into a convolutional encoder. So again, that's not a real example, but it shows that the modeling capability is there and actually very powerful. And I think it could be useful in some case. And just when you want to apply, for example, mixed embeddings, it's very convenient to use this kind of architecture. But more recently, I had a specific focus on the transformer that was already described by Vincent. And this one is a very interesting piece of work because in the paper it seems very simple and elegant, but actually when you want to make it work well and efficiently, it's actually quite complex. And over several weeks, I needed to make several implementation and training details, adjustments to make it work actually well. I mean, work at all actually. So it was very an adventure on this side. But now I can confidently say that it's a strong alternative to tensor, and there are still, I think, rooms for improvement. So if you are working on MT competition, maybe you can find a winner in OpenMT TensorFlow. We'll see. So to conclude this presentation, here is the current landscape of the OpenMT ecosystem. It's not only a project now, it's a it's an ecosystem. So you have obviously the OpenMT project, the original version with all its dependencies. That is now, we'll come back to that later. And there's also the new version of PyTorch and the TensorFlow. So this is the three main versions of OpenMT. And we try now to make some convergence between the three frameworks. So first we have the tokenization that is shared and external. And we have this new NMT wizard that can be used to launch new trainings using these frameworks. And I think this landscape is a bit an answer to the initial question of why is OpenMT still relevant 1 year later, is that we kept trying new things and adding new things to the ecosystem. And for example, there is a new framework, in this case PyTorch, we are on it. There is a new type of model, the transformer, we are also on it. So I hope we'll continue this dynamic and stay relevant in 2019, for example. And for the next months, I would say, we are going to propose this direction regarding the frameworks. So first, there is the case of OpenMT. And it's not only the case of OpenMT, it's the case of Torch itself. I think you already know that Torch has been deprecated and is now completely replaced by PyTorch. So we propose to put OpenMT in maintenance mode. That means we'll keep the same level of support, maybe keep adding some small changes to the code, but you don't need to expect big changes. For example, the transformer model will not happen in this version. And on the other hand, we have these two major implementation in PyTorch and TensorFlow, and we would like to insist on what the frameworks are good at. And I think PyTorch is very well suited for research side, because you can build a very interesting model. The framework is flexible, so we will emphasize on that. And on the other hand, for the TensorFlow, we can rely on a production-oriented mindset. We know it's very robust to implement in production, and there are a lot of tools for that. And so we will insist on this aspect for the TensorFlow version. And so if you have any proposal for a possible direction, you can, I think, ask it on the application, and we'll happy to hear what you think about this direction. And that's it for my presentation. Thank you. Questions, maybe?
Hello. I'm Sira Faradans from Forcia. At some point you said that it was important in your way of coding and publishing code and so on to not have stability guarantees on the code. Can you develop a little bit more on that?
Yeah, that means if you are building your own code using OpenMT, for example, functions or objects, it means that when you update the code, maybe it will not work. That means maybe the arguments will change, the function name will change. So you need to be careful if you are building code against this project. Just what it means. Is that clear enough?
More or less, if you're going to be publishing the code, how are people meant to use it afterwards?
So the point of OpenMT is mostly focusing on using it as a black box. That means you run the command line, and it will work. You can use the same options over time. It will also work. But if you are building a new project that includes OpenMT, for example, and call OpenMT functions, so within the code, maybe if you update OpenMT, it will not work later on. Function names will change, arguments will change, and we know that the Lua version of OpenMT is not very good to be used as a library. That's, I think, the answer to the question.
Okay, thank you.
I should say, Guillaume, that I think we're actually trying to keep the PyTorch one in a library state these days, so we have kind of clear boundaries for that aspect.
Yeah,
but we'll see if we keep it.
This rule was more for the Lua version.
Yeah, I just want to make sure. Any other questions? I just want to really quickly say, I think if you're using OpenMT, it's really because of Guillaume. He's been kind of the central piece of this project, and he's kept like all the code together and things like that. So can we give him a hand just for doing a lot of the work? Taking a break now?
Yeah, it's a coffee break, so we have 15 minutes. We already have a lot of questions, but please submit more if you want on the Slido. And we are preparing summarization of that. And the next session will be talking about your question and the feedback also on the survey. So feel free to still send things that we can have a matter for the next discussion. Thank you.